Okay. Okay.
Okay.
Oh, wait.
Now, Fang, you can take over. Fang,
Okay.
start.
Welcome, everyone. It's my pleasure to introduce the speaker, Yifan Yang from National Taiwan University. Professor Yang's research interests are both in mainly in number theory, especially module forms and the related topics like such as differential equations. So today he will talk about the monodromy of Picard-Fuchs differential equations for Calabi-Yau threefold. So please, Professor Yang, you can take over from here. Thank you.
Thank you for the introduction, and thank the organizer for the invitation. It's my pleasure to give a talk in the seminar. Okay, so the main subject of my talk today is the Monodromy of Picard-Fuchs differential equation of Calabi-Yau threefolds. So let me introduce Picard-Fuchs differential equation. I think in an earlier talk of the seminar series, some people should have introduced Calabi-Yau manifolds. So here I just say that a Calabi-Yau manifold is a complicated manifold with vanishing first Chen class. And to define the Picard-Fuchs differential equation, we needed Calabi-Yau threefolds to manifold to deform. I'm sorry, let me introduce periods first. Say, suppose we have a homomorphic differential R form, say omega, and gamma is an R cycle, then we can integrate omega against gamma and get a complex number, and this complex number is called the period. Now, suppose we have a family of Calabi n folds, say parameterized by m parameters T1 and up to Tm, then we consider unique n form on the Calabi-Yau n4. Let's say that this unique n4 n form is this denoted by this omega, which depends on the parameter T1, T2 up to Tm. Then the periods of this homomorphic n form DE or PD depends on the number of parameters, and then this will be called the Picard-Fuchs differential equation associated to the family of the Calabi-Yau manifolds. For example, one of the symplectic example is given by this so-called the Johnson family of elliptic curve. The curve is given by this equation: y squared equal to x times x minus 1 times x minus t, and here t is the parameter. And then we know that the elliptic curves are simply the I should say Calabi-Yau one-fold are simply elliptic curves. Now the homomorphic one form on elliptic curve is dx over y, and we can then a period of this elliptic curve will be the integral of this omega, the dx over y, and the integral will be from 1 to infinity. And this integral can be, say, suppose we expand with respect to t and use the beta function, then we can show that this integral is equal to pi times this 2f1 hypergeometric function 2f1 1 half 1t. So this periods ft satisfy the second order hypergeometric differential equation, this one. Okay, so throughout the talk, this theta will denote this differential operator Td over dt for convenience. Okay, so this is one of the simplest example of Picard-Fuchs differential equation. Now let's give an example of Calabi-Yau two-folds. Okay, so here is one simple example, and this is a family of K3 surface given by this quartic polynomial, and then we can show that the Picard-Fuchs differential equation for this family is again a hypergeometric, 3f2 hypergeometric. And another example of K3 surface given by this a little more complicated equation, and it's a little more complicated, but we can show that this the Picard-Fuchs differential equation for this family is given by this differential equation. And why we mention this example is that this differential equation actually appear in Aperi's proof of irrationality of zeta phi. That's why this differential equation is interesting. Okay, and now here is another example, and this is in this case it's a Calabi-Yau threefolds, and this is one of the most famous examples, and this probably one of the first examples that appear in literature about the relation between Calabi-Yau threefolds and especially the mirror symmetry of the Calabi-Yau threefolds, and we can show that this the Picard-Fuchs differential equation for this family of quantity threefold is again 4f3 hypergeometric. And in literature, there are totally 14 families of Calabi-Yau threefolds with the Picard-Fuchs differential equation are hypergeometric of this form, where the local exponent at 0 are always 0, and the local exponent at infinity are a1 minus a, b, and 1 minus b for some pair of rational numbers a and b. Here the parameters a, b, and their the geometric invariance of this 14 family of hypergeometric Calabi-Yau threefolds are given by this table. Here we only list 6. And the others can be found in literature. Here the notation H will be denote the hyperplane class, and so that the H cube will be the degree of the Calabi-Yau threefold, and the C2 dot H is the second Chen number, and the C3 will be the order number of the Calabi-Yau threefolds. Okay, so the quintet threefold is the first case where the parameter A is 1/5 and the parameter B is 2/5. Okay, and now we introduce the monodromy of differential equation, and we will explain the motivation later on. Let me introduce monodromy first. Okay, suppose we have a linear ordinary differential equation, say given by this general form of a differential equation, and suppose that all the singularities are regular. Okay, and now that L be the solution space of this differential equation, now we consider, say we have a closed curve not passing through any singularities. Then we can consider analytic continuation of the solutions along gamma, and this will give rise to an automorphism of the solution space, and we call automorphism monodromy. So in this way, we get a monodromy representation of the fundamental group P1C minus the singular points. And so in general, we usually choose a basis, fix the basis of this solution space, and write the monodromy group as a subgroup of G O and C. Okay, let me give some examples first. Okay, say this example is the example the general family of elliptic curve. We have seen earlier that this is a hypergeometric 2f1 hypergeometric. Now since this is a hypergeometric differential equation, the solutions are well known. And in this case, one solution is given by this 2f1 1/2 1/2 1t. Let's call this one y1 y1, and because of this differential equation has a symmetry between t equal to 0 and t equal to 1, so we have another solution y2, which we denote by y2, which is 2f1 1 half 1 half 1 1 t. Now this differential equation, the local exponent at 0 are 0. Okay, so this means that this solution, this differential equation has a solution that is homomorphic at 0, and another solution which is which has a logarithmic singularity near t0, t equal to 0. So, and in this particular example, we can show that this y2. Okay, so y2 should be near t equal to 0. This should be a linear combination of one solution which is homomorphic, and the other solution is has a logarithmic singularity. In this case, we can compute using some analysis and then show that the y2 is actually equal to this kind of the local behavior y2 near t equal to 0 should be of this form, which is log t times constant times y1 plus some a function that is homomorphic near t equal to 0. Okay, so using this information, we can compute the monodromy around t equal to 0. So around t equal to 0, when we talk about monodromy, this means that we consider the closed curve around t equal to 0 and the small curve, and when we travel around this curve, the solution. Let me put it this way. Initially, we have a pair of solution f. I'm sorry. Notations y1 and y2. So initially, we have a pair of solution y1 and y2. Okay, and so because the differential equation has singularity at t equal to 0, this pair of solution is valid only initially only valid some in a small disk that is around this point, but not at this point t equal to 0. So, but now we move along this curve. So we have a continuation from this disk to this small disk, and again we move from this small disk to this small disk. So from here to here we get another pair of solution that agree with the initial solution y1, y2 on the overlap, and we move again, and eventually we'll come back to this initial point. But because the solution, the starting solution y1, y2, even though we can, we can analytically continue the solutions, but when we come back to the original point, the solution may not be the same as the initial ones. That's why we call why we have a monodromy, because when we come back to the original point, the solutions are changed. But the solutions are at the end, the function we get are still solutions of the original differential equation. So this means that when we come back to the original point, then y1 and y2 becomes y1 tilde and y2 tilde. This y1 tilde and y2 tilde, they are still solution of the differential equation. So, and since y1 and y2 are basis of the solution space, this y1 tilde and y2 tilde should be a linear combination of the y1 and y2. Okay, so in this way we can we see that we can realize the monodromy as a 2x2 matrices. So here, let's work out this particular example. Okay, so when we travel from okay, when we travel from along this small curve, a small circle, let's say circle. So from this point to this point, then this means just means that we change the argument of this t, and initially the argument is 0, but when we travel back to along this small circle back to the original point, and the argument is changed by 2 pi. So this means that the t is changed to t times e to 2 pi I. Okay, so that's the effect of the analytic continuation. We change t to t times e to 2 pi I. Now let's go back to the original expression for y2. Now y2, I'm sorry, y1. Okay, y1 is a homomorphic near t equal to 0. So y1 is not changed. Y1 is still y1. Yeah, because this is a homomorphic function near t equal to 0. But the y2 is changed to, okay, remember that t is changed to e to 2 pi I times t, and the y1 is not changed. So this becomes 1 minus 1 over pi times y1 times log t plus 2 pi I. I'm sorry. This tail is a homomorphic near t equal to 0, so this is not changed. Okay, so totally, let's simplify, and we will see that the y2 is changed to, let me see, minus I y2, I'm sorry, minus 2i times y2 plus y1. Okay, because I'm sorry. Okay, so this term together is the y2 and the 2i y1. Okay, so in summary, the solution y1 is not changed when we travel around t equal to 0, but 2 is changed to y2 minus 2i times y1. Okay, so here for simplicity, let's change the basis to iy2 and y1. So iy2, remember y2 is changed to y2 minus 2i y1. So iy2 is changed to iy2 plus 2y1. Okay, so in summary, the original solution iy2 and y1, they changed to iy2 plus 2y1 and y1. Okay, so in this case, the monodromy matrix will be 1, 2, 0, 1. And similarly, around t equal to 1, we can show that with respect to this basis, the monodromy matrix is 1, 0, minus 2, 1. Okay, so this is the monodromy, and now we know that these two matrices, and I should say along minus I2, they generated this gamma 2, the principal congruence subgroup of level 2, and so this is, so in other words, the monodromy group of this 2f1 hypergeometric function is gamma 2. Okay, now we see why we are interested in monodromy group. Here, suppose that we set tau equal to the ratio of two solutions, iy2 over y1. And initially, this is a function of t, but now we can consider the inverse function. We consider t as a function of tau. Then now we can okay. So let me remind you that this around t equal to 0, this tau is changed to tau is equal to iy2 over y1, and then this is changed to iy2 plus 2y1 over y1, and then this is equal to tau plus 2. Okay, so around t equal to 0, tau is changed to 2 plus 2, and around t equal to 1, tau is changed to tau over minus 2 tau plus 1. Okay, now we consider t as a function of tau. Because t as a function of t is of course homomorphic. Okay, so the t is invariant under monodromy, any monodromy. Okay, but tau is changed. Sometimes tau is changed to that we mentioned earlier. Sometimes tau is changed to tau plus 2, and sometimes tau is changed to tau over minus 2 tau plus 1. Okay, so in general, tau can be changed to a tau plus b over c tau plus d, where a b is in gamma 2. Okay, so it's invariant under monodromy, but tau can be changed to a tau plus b over c tau plus d for some a b c d in gamma 2. Okay, so suppose we consider t as a function of tau, then that is invariant under monodromy, but tau is changed to a tau plus b. Tau may be changed to a tau plus b over c tau plus d. So this means that we have t of tau equal to t of a tau plus b over c tau plus d for any ABCD in gamma 2. Okay, in other words, t is a modular function on gamma 2. And similarly, we can show that the period as a function of tau, this is a modular form of weight 1 on gamma 2. And so this is in fact a classical identity where we have this identity theta 3 tau copy theta function theta 3 squared equal to 2f1 1 half 1, and theta 2 raised to 4, and over theta 3 raised to 4, and this is the modular function on gamma 2, and this is the modular form of weight 1. On gamma 2. Okay, so this is our y1, and this is our t. And similarly, for the K3 surface we mentioned earlier, the first example, in the first example we can show that this differential, the 3f2 hypergeometric function, hypergeometric differential equation is actually the symmetric square of this 2f1. And for this 2f1, we can compute that the monodromy group is gamma 02 plus. Okay, so in this case, the solution of this differential equation, the third order case, the differential equation, let me say in this way, the solution of this second order differential equation will be a modular form of weight 1. Okay, so then because of this is differential equation is a symmetric square of this differential equation. So this solution of this 3f2 will be modular form of weight 2. Okay. And for the case of for the second example of the K3 surface, the differential equation is actually the symmetric square of this differential equation, and in this case, the monodromy group is gamma 06 plus the accumulated involution W6, and so the solution of the original third order differential equation can be written in terms of a modular form of weight 2 on this group gamma 06 plus the accumulated involution W6. Okay, so in general, actually we have the following general result, which says that if we have a subgroup of S2R that is commensurable with S2Z, and suppose we have a modular form weight K and a non-constant modular function T, then F and up to tau raised to K times F as functions of T will satisfy K plus first order linear differential equation with algebraic functions of T as coefficients. Okay, so in the previous 3 examples, we have the first example we have second order, and the solution can be expressed in terms of modular form weight 1, and then the second example and the third example, where the differential equation third order is we have the solution can be expressed in terms of modular form weight 2. Okay, so that agree with the theorem here. Okay, so the natural question to ask is that for the quintic threefold case, the 4F3 hypergeometric differential equation, is this differential equation somehow related to classical modular form weight 3? That's actually the motivation for my work with Professor Yu and Yao-Han Chen. And so for this question, the answer is actually no. Actually, this is, can be answered by the following theorem of Beukers and Heckman. They show that up to conjugation, the theoretic closure of a monodromy group of an Nfn-1 hypergeometric function have the following 3 possibilities. The first one is that is a SLNC. That's the theoretical case. Now suppose that the differential equation is somehow more special, then the theoretic closure of the monodromy group can be symplectic or orthogonal. And in a very special case, monodromy group can be finite group. And moreover, they provide an algorithm to determine which one. So using their argument or algorithm, we can show that for the quintic threefold case, the theoretic closure of the monodromy group is symplectic. Okay, so in other words, the differential equation in the threefold case cannot come from modular form or weight 3. Yeah. So this the question is by Beukers and Heckman's result. Okay, and here we can give a very quick explanation why the monodromy group is symplectic and not a SL. Here we can show that for the 14 hypergeometric families, we can show that the locus moment of the differential equation at 0 are all 0. So there are 4 solutions of the form, and the following form. The first one is homomorphic near t equal to 0, and the second one has 1 log, and the third one has 2 logs, and the third one, the last one has a log t cube. And we call such a basis the Frobenius Frobenius basis near t equal to 0. Okay, that's because we this basis come from solving the differential equation using Frobenius method. So that's why we call this basis the Frobenius basis. Okay, so for the 14 families, we can show that the Frobenius basis satisfy this identity. So determinant of y0, actually, I should say the Wronskian of y0 and y3 equal to the Wronskian of y1 and y2. Okay, so and any monodromy must preserve this relation. So up to conjugation, the monodromy group must be in the symplectic group. That's one quick explanation why the monodromy group is contained in the symplectic group. Okay, so so now we can introduce our results on the monodromy of the Picard-Fuchs differential equation for Calabi-Yau threefold. So we show that for the 14 hypergeometric families, the monodromy group relative to the Frobenius basis are given by these two matrices. The first matrix is the monodromy around t equal to 0, and the second matrix is the monodromy around the other finite singularity y over c. And the interesting thing or the significant thing about this result is that all the entries can be written in terms of the geometric invariance of the Calabi-Yau threefold. Here, for example, here the entry, the number a here is actually the Chen number. I'm sorry, all your number times this There3 divided by 2 pi cube, and this number b is the second number divided by 24, and the d is the degree of the Calabi-Yau threefolds. Okay, so every entry in the monodromy can be expressed in terms of the geometric invariance of the Calabi-Yau threefolds. I think that's the interesting part of the result.
Zeta 3 is coming.
And sorry?
Zeta 3 is coming in there. Why?
I'm sorry, I didn't hear.
Zeta 3 in the value of A.
What is H3? H sub 3.
H sub 3, not where?
D is equal to H sub 3. You already sub 3 before.
Yeah, D is the degree. Yeah, D is the degree of the Calabi-Yau threefold.
Yeah.
And D3 is all the number. And this is the second Chen number.
Yeah.
Yep.
For data 3.
Any other questions?
Zeta of 3 is the value of
zeta function. Yeah, I'm sorry. Yeah, zeta 3 is the Newman zeta function. Zeta 3. I'm sorry. Yeah, this is the Newman zeta function. Yeah, so it's interesting that the spatial value of the Riemann zeta function appear in the entry of the monodromy. Yeah.
What is the effect on the group generated? Because zeta 3 is expected to be transcendental, I think.
Yes.
So
okay.
The second matrix involved transcendental numbers. It's sort of strange.
Yeah. So we this result is only kind of verification, we don't have any explanation why the monodromy of this form. We don't have any explanation. We just verify. I should say we just verify that the monodromy are given by these two matrices. Yeah, we don't have any explanations. Yeah.
You should say this will be sitting inside the SP4 and all that. You do that later?
Not yet. These two matrices are not yet. We need to change basis.
Okay.
I mean, not in the standard symplectic. Of course, this is symplectic because not a standard symplectic, but after some change of basis. We will mention that later. Okay, so here we can briefly explain the idea in the proof. So the differential equation have three singularities, and say the singularities are 0 and 1 over c and the infinity. And the monodromy matrix will satisfy a single identity relation. The product will be equal to the identity. Okay, the matrix for the monodromy near 0 is trivial to determine because we have the explicit basis and the Frobenius basis. So this is trivial to determine. Okay, so to determine the monodromy matrix.
Middle of a seminar.
Okay, so to determine monodromy group, we only need to determine one of them. So here we compute M infinity instead of M instead of monodromy near 1 over c. And in general, monodromy matrix with respect to local Frobenius spaces are always trivial to write down. So we only need to determine the relation between the Frobenius spaces at 0 and the Frobenius space near infinity. Sorry, any questions?
No, continue.
No comments.
Just continue.
Okay. Okay. So here the proof of the only thing we need is to determine the relation between the two Frobenius spaces near 0 and near infinity. That's the part we need to determine. Okay, for this purpose, we introduced the following function FTH, which is actually kind of deformation of the hypergeometric function. Okay, here the function f is given by this expression. If h is equal to 0, then this is simply the 4f3 hypergeometric function that is a solution of the differential equation. And we can show that if we take the partial derivative of this function with respect to this deformation parameter h, then we will get all the solution y1, y2, y3. If we differential once, then we get y1, and then we differentiate twice, then we get y2, and so on. Okay, so in general, we can express the solution as the derivatives of this function f. We can easily show that. Now this function FTH has the following bonus type integral representation. Okay, and here the path of integration is from minus I infinity to I infinity, such that the pole of this factor pi over sine pi s lie on the right of the path, and then the pole of this function, this product, lie on the left of this path. Okay, this function f have the following integral expressions, and now we just by using standard complex analysis argument, we just move the path of integration from this original path c to the far left. Then we can determine the ratio between the Frobenius spaces at 0 and also at infinity. Okay, so in this way we can define M infinity and also M1 over C. Okay, so that like we mentioned earlier, the Monodromy matrix in the previous result are not in the standard symplectic group. So here we change the basis to the following basis. This basis, we can show that with respect to this basis, the monodromy matrix will be these two, and they are in symplectic group, and the standard symplectic group SPO for Z. Okay, here the D again is the degree of the Calabi-Yau threefold, and the K is another invariance given by this. Okay, this time the ZR3 disappear and the all in the number disappear. So we degree and this second Chen number. Okay, and one interesting thing about this matrix is that they are contained in the following congruence subgroup: gamma D and the GD of D and K. Here the notation gamma D1 D2 denotes the symplectic matrix, integral matrix, such as the matrix is come to matrix of this form module D1 and congruent to this matrix module D2. A little complicated. Okay, and here I should make some remark because the computational monodromy matrix well, we are not the first one to compute the monodromy. The first, for example, candidates did the OSA, Green, and the their paper already determined the monodromy for the quintive case, and the claim and the Titan using similar argument determine the monodromy of several other hypergeometric cases, and Doran and Morgan show that there is a basis such that the monodromy matrices are given by these two. Okay, linear algebra, and so they actually didn't show which basis will give these two matrices. So our result kind of improved results. Okay, so now, let me mention the non-hypergeometric cases. In literature, there are many hundreds, like or thousands of family of Calabi-Yau threefold with non-hypergeometric Picard-Fuchs differential equation. And for those differential equation, we don't have any method to determine monodromy rigorously. We can perhaps compute numerically, but there's no method to rigorously determine monodromy. Okay, using some numerical idea, we can show that in every case there's always a basis such that the monodromy around 0 is of this form, the same as the hypergeometric case. Okay, 1 1 0 0 0 1 0 0 and D 1 0 and 0 mass K 1 1. Here the D is always the degree and the K is always this number, another geometry invariant. So in all cases, we can always find a basis such that the monodromy around 0 is of this form, and there's another singularity where the monodromy is of this form. Okay, and but here I want to mention that sometimes the monodromy group are not in symplectic group, but in the paramodular group instead. Okay, when we compute work on our project, we actually didn't have any knowledge about this paramodular group. We have never heard of this, but later on we found that the monodromy group we computed are actually in the so-called paramodular group. So let me review the definition of paramodular group. Let n be a positive integer, then the so-called n paramodular group denoted by power n is the creation of integral invertible matrix such that the M transpose times this matrix 0j max j0 M is equal to 0j max j0, where j is n001. Okay, so when n is 1, this is simply a symplectic group SP for Z. Okay, but when n is not 1, then this is a little different. And when n is 1, we know that this the quotient space of upper half space H2 quotient by this symplectic group is the modular space of principally polarized abelian surfaces. And then analogously, for the n paramodular group, the quotient space of H the z-equals upper half space quotient by this power n will be the modular space of n1 polarized abelian surfaces. Okay, and in practice, we often conjugate this power n by this 100j, such that this group is contained in the standard symplectic group. Okay, then this gamma n is actually of this form. We can show that the gamma n is actually creation of matrix of this form, where the star represent integers and the n is the integer we are given integers, and so gamma n is an integer of this form and contained in the standard symplectic group SP4Q. Let me just give one example where the monodromy group is contained in the paramodular group. Okay, so here this is one of the examples, and we can show that the monodromy group is contained in the gamma for the 4 paramodular group. Again, we stress that our result is numerical. We don't have any rigorous method to determine monodromy. Okay, so here's one example where the monodromy group is not in the SP4Z, but in the paramodular group. Okay, now I have still 10 minutes, so let me mention some recent result. Okay, so our result only give the generator of the monodromy group, but from our result it's not clear whether the group generated by these two generators are finite index or infinite index. This is actually a very deep question, and so here we use the terminology introduced by Fuchs and Mary and Sarnak. They define the so-called Ting subgroup and the arithmetic subgroup as follows. Suppose we have subgroup gamma of SP4Z, then we say the group is thin, the subgroup is thin if the index is infinite. Otherwise, we say the subgroup is arithmetic. Okay, I think the reason why we say the finite index are arithmetic is that for SP4Z, we know that every subgroup finite index is a congruent subgroup. So I think that's probably the reason why such group is called the arithmetic subgroup. And so in 2014, Rav and Thomas showed that 7 of the 14 families are thin. In other words, the index is infinite for this 7 families of hypergeometric differential equation, and the Ting and the Venkataramana show that among the 7 remaining cases, 3 are arithmetic. And finally, Ting in 2015 showed that the remaining 4 are all arithmetic. So in 7 are Ting and the 7 are arithmetic. I think Ting will give a talk on this classification later, probably next week or sometime later. And okay, so to summarize our talk, we just want to ask the following question: and are there any legal module form or paramodule form behind those Picard-Fuchs differentiation? So that's the end of my talk. Thank you very much for your attention.
Thank you very much. There are any questions or comments?
Well, the Jigger modular forms may come up, or paramodular forms. We have now, I think, about 12 examples, Jigger modular forms of weight 3, weight 4, rank 4 and weight 3. About 12 examples.
But in those examples, simply means that the L functions are,
yeah. So we don't have this because there's 14 families, and you go to the mirror side, then you get Calabi-Yau threefold of type 1, 1, 1, 1. So you get Picard-Fuchs of order 4. And then for those, not everybody will have Jigger modular, but we have about, so it's not Calabi-Yau threefold, but at the motivic level, we have about 12 examples where Jigger modular form of weight 3 will come up.
Well, that's I asked earlier. So in those examples, I think that means that the L function of this legal module form or paramodule form coincide with the L function of this
Andrianov L function, yeah.
Yeah, but can we express the solution of this Picard-Fuchs differential equation in terms of?
No. This is more of a representation theoretic approach and or motivic approach. So nothing is very explicit.
Yeah.
Okay, any other questions from audience? Okay, so if there are no further questions or comments, let's thank the speaker again.
Hello.
Oh, yeah.
Many of the Ting groups may be non-discrete also, right? Non-discrete.
Non-discrete.
Is it possible?
I think the
Group.
Okay, many of
so the non-discrete means non-discrete. The definition is the orbits of any object has no limit point, or is that's the definition
in the topological sense? No,
I think you have to ask that to Sandeep. Sandeep, he's giving a talk, I think, later.
Okay.
Okay.
Thank you.
Any other question? Okay. No. Okay. So. Okay. Thanks. Thanks. Let's thanks the speaker again.
Thank you very much. Yeah.
So I think we will end this talk.
Okay, so that's the end. So as I asked before, how long you know this seminar will go on, because I'll be away. It's part of July. I will have no access to Zoom.
It will be for 2 months more.
Really?
2 months.
Because this in the cottage is no access to Zoom, no internet.
2 months
2
more.
months more, 2 months more, my God. Okay. Okay.
Okay.
See you.
Yeah, bye.
Bye.
Thank you. Yeah, see you later.
Bye.
Yeah. Bye.
Bye.
Thanks, Yifan, and thanks, Fang, for chairing this talk.
Oh,
Yeah, thank you very
no
much.
problem. My pleasure.
Okay, see you.
See you.
Pawan,
See you.
can you stop the live stream and recording?
Okay.